Right. So we'll continue from where we left. So for the parabolic equations, where you have a transient equation, for example, transient heat conduction equation, we discussed that alternatively we can have a two-step process. So for one time step, we can break that one time step into two parts. Okay, half a time step and then another half time step, and then in the first half we can take the x direction as implicit. Similarly, in the second half we can take the y direction as implicit. So that is called the alternating direction implicit method. So that is useful because that allows us to use the tridiagonal matrix algorithm in without the need for an iterative algorithm. But the check is that for the first half you have to make sure you do it in the x direction, you make it implicit, and in the second step you make the y direction implicit. So that gives another scheme which is alternating direction implicit. Now in this scheme ADI, we have this becomes the good thing about this scheme is that the truncation error is order delta t squared along with delta x squared and delta y squared, whereas for backward time center space and forward time center space we saw that we had order delta t schemes. In space they were second order, but in time they were first order. So the good thing about this scheme is that it is indeed second order in time, but that is only true for the 2D case. For 3D it again becomes order delta t accurate. So you have to remember that if you are using ADI, the benefit of time accuracy is only achieved in two-dimensional problem, not 3D. In reality everything is 3D, but there are some problems which you can approximate as two spatial dimensions. Now the other benefit of this is that the 2D case for ADI is unconditionally stable, whereas for the 3D it becomes conditionally stable. So you can check for yourself by writing the amplification factor for each half time step and then multiply them as we discussed last time. Okay. Now just like alternating direction implicit, we also have something called alternating direction explicit. So it's called ADE. So in this case I will write the discretized equation. Now a typical explicit equation is where you write the for the two-dimensional transient heat conduction equation. On the left hand side we have theta n plus 1 ij minus theta n ij upon delta t, and since it is explicit, so you have on the right hand side theta n I minus 1 comma j, and then you have so everything is at the nth time level. And then we have a term for this is delta x squared, and then we have a term for delta y squared. Everything is at n for y as well. This n is not power but for the time. Now with ADE, what we do is we make some changes to the scheme. Vishal, there is some issue with this, later you can check, so it's pointing somewhere and writing somewhere else. Right, so what we have done is we have made changes here, here, here and here, so we have written that. So for 2 theta ij we have broken that into two parts, and one of them we have written at n plus 1th time and the other is at nth time, and the I minus 1 and j minus term j minus 1 term are both at n plus 1th time step. See, right, so this is different, right? So this is called alternating direction explicit. So there is a difference. If it was exactly the same, then it would have been simple explicit, right? So here, so this is step number 1. It is in fact 2-step process. So what we see from here is, if you look at the way you evaluate the points in explicit scheme, basically you have to decide an order in which you will evaluate, right? So we go from left to right, bottom to top, let us say. So in that case, we evaluate this point, then we go to the right point and so on, and then we complete all these points, then we start going up. So let's say we are evaluating this point, which is a square. So for that theta, which is I comma jth point, so for calculating theta n plus 1 here, what we are doing is, for the I minus 1th point, which is this one, and for the j minus 1th point, which is this one, you are using n plus 1th. This is not an iteration, this is time step. So you are using n plus 1th, and the reason we can use it and it is still explicit is because we have already calculated the left and the bottom point in our loop. So the theta n plus 1 value for these points is already available now. Okay, so it is still explicit. So explicit is the unknown value goes on left and the known values go on right. So here, since the I minus 1 and j minus 1 points have already been calculated, they can go on the right. And for these points, the diamond points, which are not evaluated yet in the loop, they are still available. The latest value available for them is for the nth time. So you use that. It is very similar to the idea of iteration, but this is not iteration, this is time step. So always remember that difference between an iteration and a time step. They are different loops. So we are talking about explicit expressions here. And in the second time step, so in the first time step we go this way, and then we go this way. So basically left to right, bottom to top. In the second time step we will go top to bottom, right to left. So in the second time step we will go like this. So that becomes step number 2. So in that case, on the right hand side you will have the I plus 1 comma j term will be at n plus 1, and the I comma j plus 1 term in the second expression will also be at the n plus 1th time. So just change this and this to n plus 1, and all the other terms stay on the nth time. Easiest way to understand is you think of whatever has already been calculated in the loop is at the n plus 1th time, and whatever is not calculated is at the nth time. Of course, theta at the I comma jth point is at n plus 1 because you are evaluating that n plus 1th theta. Well, if you just go from bottom to top every time, then remember that bias we talked about. So the errors will tend to accumulate. So it's always good to take both directions. That is one reason. Otherwise, you tend to get a bias in. So whenever you write these loops, you go in one way and then the other way. So that is the primary reason. For ADE, we were doing lines horizontal and vertical. That was a different reason because we wanted to make it implicit in both directions separately. But here it's completely explicit. So the reason we are doing it is just to remove the bias. So this alternating direction explicit, the good thing about this is that it is unconditionally stable. But a bad thing about this is that the transient values can be quite erratic. So, I can show that through a graph. So, let us say we are talking about the theta value at let us say I comma jth point, some I comma jth value as a function of time, and this is the exact solution. Hypothetically speaking, let us say I knew the exact solution. So, if you use ADI, alternating direction implicit method, then you would get something like this. Now, this is not equal to the exact solution, there is some error because you have a finite delta t. So, you will have an order delta t squared error, let us say in this case. So, there will be some error, but if you take the alternating direction explicit, you would get a solution which looks like this. Okay, so, the transients are quite erratic, but if you look at the steady state solution, when the solution actually reaches a steady state which does not change with time, it will approach the same value or within some error. So, if you are trying to predict the transient solution accurately, so how is the temperature of the body changing with time, then you would not go for ADE, but if you want to look for the steady state solution, then you can use ADE. Now, the question you might ask is, then why should I be using the transient equation if I want the steady state solution? I would use the elliptic equation instead, the Laplacian of theta equal to 0. But if you remember the problem number exercise 2 in lab number 3, that was exactly what it was, that you can use a transient method which is actually called a false transient method to solve the equation. So, you even if you want the solution to the elliptic equation, you parabolize it by adding a del theta by del t term on the left hand side and some alpha value to be multiplied on the right hand side, and you solve it using an explicit method. So, that ways you do not have to write an implicit solver, you can simply use an explicit method and let it run to steady state. Steady state means the solution will stop changing with time. So, that if you have a transient solution solver available with you, you can use that to solve a steady state problem as well. Okay. So, please try lab exercise 2 in lab number 3, and that will make things clear. If not, then you can ask me for help. Right, now the final sort of scheme I will want to discuss. Now, there are many schemes available. ADI. So, I am confusing you with the colors here. So, on this slide, this is red one is ADE and the black one is exact. So, this ADE is unconditionally stable. Now, this one is called Hopscotch scheme. Now, as I said, there are many schemes available. So, I am just giving you a few to convey the ideas. So, we have conveyed the idea to you of doing horizontal and vertical lines in ADI, which allows you to use the tri-diagonal matrix algorithm to solve for problems which are in larger number of dimensions, where TDM is not generated, but you can generate that by this idea of ADI. Similarly, ADE can be used where you go in once from left to right, bottom to top, and then the other way, and you can use explicit methods to generate solutions for steady state problems. And again, this ADE in fact sometimes can give you order delta t squared accuracy. So, that is good in that sense, but the errors are quite erratic initially. So, we will not go for those schemes for transient solution. Now, hopscotch is another approach which is used a lot in CFD, where we tend to write an implicit expression, but that actually is explicit. So, I will show you how. So, what we do is we color the points, so to say. So, every alternate point So, we have the red points and the blue points here. So, the red points will be evaluated first. So, for red points we will use an explicit scheme. Again I am not writing the complete expression, but it is completely explicit, all at the nth time on the right hand side. And then what you do is, for the blue points you write a completely implicit scheme. But actually this step number 2, the blue step, is also explicit, and the reason is because once you have evaluated the red points, now look at the blue step, the second step. On the right hand side we have theta I minus 1 comma j at n plus 1. Now let us say this is the blue point we are talking about, this one. So I minus 1 is this one, but that is a red one, and that red one already has been calculated here. So that is already available. So that is sort of explicit in the sense that it is already available. Okay. Similarly, the I plus 1th point is also available, j minus 1, j plus 1, all are available. So the blue step actually becomes an explicit step. So rather than going every adjacent point, you change the order, you go, you loop over the red points using an explicit scheme, and then you loop over the blue points using an implicit expression, but it actually becomes explicit. So this is called a hopscotch because you are sort of jumping, hopping. This scheme is also unconditionally stable, so that is the good thing about it. So every scheme that is being introduced has to have some benefit, otherwise there is no point. So this is also unconditionally stable. And a similar approach is used in to generate a scheme called coloring scheme. Now again, coloring comes from the point that I was coloring them as blue points and red points. So they call it coloring scheme. Now we will go back to iterations. Okay, let us go back to iterations in, let us say, a steady state solution. So in iterations, if you remember Gauss-Seidel method, what we were doing was we were following this order. We do this point, then we do the next point, but this time again we are doing alternate points. We have a red point, we have a blue point. So even in iterations we follow this approach. So first we do the red points and then we do the, so we update red points in our iterations in one sweep, and then we update the blue points. Now you may ask, why are we doing this? And the primary reason for doing this in iterations is we want to parallelize the work. In computing nowadays, running a serial code is very slow. We do not run codes on a single core. We have many computers or many processors or processing cores working together, even thousands of cores. That is the reason we have supercomputers. So if you can parallelize a job, if I have 100 bricks to move from here to there, if I do it alone, I might have a limitation in how much time I take to move from this end to that end and so on. But if I have 50 people working, then that gets completed in 2 steps, or 100 people working, just 1 step needed. So I can run the thing quicker. I might need more computing power, but if my aim is to get the job completed quickly, given that I have computing power available at my disposal, then I can in fact, if I can parallelize the code, it is beneficial. So using this approach, what you can do is you can parallelize this effectively on 2 codes. In fact, you can generate more colors and then or more sort of red, green and blue and so on, and then you can do it in multiple codes, because when you are doing it on 1 core, for calculating the red point you would need the blue point information, and that you can use from the previous old iteration. Similarly, when you are using the blue point, you will need the rate point information that you can use from the previous iteration. So, that lets you update all the points at the same time, or I mean two codes can work together. So, the work gets completed in half the time, and if you have more codes working together, if you have 3 colors or 4 colors, you can get that completed in even lesser time. Okay. So, right, so we will stop here for today. So, that is the end of iterations and all these advanced schemes discussion. From the next class, we will go to the hyperbolic problems, and then we will go to fluid mechanics problems.